Welcome everybody to this week's Astronomer episode. We are here to answer all your questions about science, the universe, and everything. And I'm Stefan. I'm a student at the Institute of Astronomy in Cambridge. And today with me I have Kat. Do you want to introduce yourself and tell us a bit what you're doing?
Yeah, hi. My name is Kat, and I'm also a PhD student at the Institute of Astronomy. And I research the effect of throwing asteroids and comets at terrestrial planet atmospheres and seeing what they do. Yeah, very, very happy to be here today.
Nice, okay. So we got one question really early today that was asking, what is a nebula? So do you want to tell us a bit about what is a nebula?
Yeah, so nebulas are really cool. So they're basically, they're clouds of dust and gas in space. And what's kind of cool about nebulas is that there's different types of nebula, and they're actually completely different physical objects. So you get things called planetary nebulas, which are kind of when a star reaches the end of its life and dies and explodes and throws out a whole load of material into space. But nebulas can also refer to entire galaxies. So like the Andromeda Nebula you might have heard of is the closest galaxy to us in the Milky Way. And the reason they have the same name is that back when sort of very early astronomers were looking through their telescopes, a small cloud of gas and dust quite close to us doesn't look all that different from an absolutely massive cloud of gas and dust really, really far away. And so they called them both nebulas. And then many years later, we realized that actually they're completely different things, but now they're stuck with the same name.
And when we're talking about Andromeda, we have just had a question, I think, on YouTube. Why is Andromeda moving towards us while the rest of the universe is expanding away? And that's indeed a nice question. So we know that by kind of looking at lots of galaxies, that almost everything is moving away. And we figured out that it's essentially due to the expansion of space itself. So space is expanding, and everything, like even, I don't know, the moon would be expanding away from us if it wouldn't be pulled towards us by the gravity. And so all the objects that are kind of far away are moving away from us, and the objects that are close to us would be moving away from us as well. But the further away, the faster this movement. So the closer you get to us, the slower this movement is, and the more impact does kind of normal movement of gravitational attraction have. So Andromeda Galaxy is moving away from us with about 50-ish kilometers per second from expansion of space, but it's also being attracted from the gravity from our Milky Way, so it's moving towards us kind of in the sun. But yeah, so it's kind of, the gravitational attraction is stronger than the expansion of space. And what's actually interesting, this is only true for very few galaxies. So almost all the galaxies will be expanding away from us and will never kind of collide with us, let's say, except for Andromeda, the Magellanic Clouds, and a few other smaller galaxies that are part of what we call the local group. So yeah, that's kind of our company. Yeah, we got one question on YouTube. I'm sorry, when I miss some questions, I'll try to kind of write them down and ask, go through every question. But if there are too many, we might miss some, and you might have to ask again one day. Okay, so we got one about Planet 9. Do you want to say something about Planet 9?
Yes. Okay, so for people who don't know, Planet 9 refers to the idea that there might be another planet in our solar system. So we've got all the planets you've heard of, Mercury, Venus, Earth, Mars, all the way out to Neptune. And we did have Pluto, and that was the original Planet 9, and then it got demoted, and it wasn't Planet 9 anymore, and some people were very sad. But Planet 9, I think what people are asking about here is this idea that there is another planet further out in our solar system that we've just never seen. And whether or not this actually exists is questionable. There's some evidence from the orbits of objects in the Kuiper belt, so sort of things that might become comets one day, so very far out, very cold, very, very far away from us. And there's some evidence from their orbits that there might be something big hiding behind them and sort of giving them a nudge every so often when they get close. But we've never detected it directly. And there are some plans to look for it. No one has found it yet, but it might be out there. And if it is, it's probably something about the size of Jupiter, maybe a bit bigger.
Oh, that's quite large compared to like Pluto.
Really big. But because it's so far away, it's very dark, so we can't see it. So it's not like we could look out into the sky and see something bright and go, ah, yes, planet 9. So we need to look for it maybe by it getting in the way of a star and sort of blocking out that starlight for a little bit, or I think there's some other clever ways people want to look for it. But yes, may or may not exist.
Do we have any idea what it could be made of? Or what would you expect?
So if it's anything like something the size of Jupiter, it will almost certainly be similar to Jupiter. So it will have some kind of dense core and then probably a lot of gas, likely hydrogen, helium, maybe some metals. But it will be much, much colder than Jupiter because it will be so far away from the sun.
Okay. We got one really cool question by, I think, Natalia, was it? Asking about if the planets in Star Trek are real planets. And that's actually a really nice question. So when I thought, okay, if I design a sci-fi series, I might as well include planets that are actually there. But the cool thing is, when they made Star Trek, the original series, and I think the Next Generation as well, this was like before 1995. So we didn't actually have discovered any exoplanets when they made kind of Star Trek. So the authors of the show must have made up some exoplanets. And I think it must have been a surprise, well, probably not a surprise, but I'm sure they were happy when we actually discovered exoplanets. So in 1995, Pegasi 51b was discovered, which is kind of the first exoplanet that we found. And yeah, before then we didn't have any. So the ones in Star Trek aren't really real, but there are some that are actually quite close to real objects. One example I looked up is the moon, actually, Andoria, which is in Deep Space Nine and I think a bit in Star Trek Enterprise, which is pretty close to the Jupiter moon Enceladus. So it's kind of actually I don't know the details, but it's quite close to that moon, and I think Enceladus also could, in theory, have water below its surface. I think there's like a mission going there. Are there any stars which have more planets orbiting than our own sun?
Almost certainly. The universe is a very strange place.
Now let me count a TRAPPIST. How many did TRAPPIST have? 1, 2, 3, 4, 5, 6, 7. Okay, almost. But I'm
not quite.
I'm pretty sure that there are systems with many more planets than ours. Because I mean, it would be really surprising if it would be the one system with so many planets. And given that we already found one with 7 planets, and given that it's really hard for us to find multiple planets in one system, because if there's one planet, you see like, oh, the light curve of the sun, it has a one dip where the one planet goes in front of it. But you have lots of planets, it gets really messy and it gets really hard to find. So actually finding lots of planets is really hard. So I suppose I'm confident that we will. Well, I mean, I'm confident there will be a system with many planets. So what do we have?
Which star has the most exoplanets orbiting it? Well, we don't know that because we haven't found them yet.
I think TRAPPIST is the one that we like, the discovered one where we have to discover the most, except Sun. Yeah. I think, yeah. And we got a few.
It's easier for TRAPPIST-1 because it's relatively close to us, and all of its planets are relatively close to the star.
Oh yeah, that's a good point. Actually, so I put up the slide here.
Yeah.
Yeah, and all kind of depends. Like the 7 planets that are there, they are all closer to their sun than our Mercury is to our sun. So it's ridiculously close to the sun, which means, of course, the planet is so close to the sun that it makes a big shadow that we can see, which is nice for us. And we got a few questions about life, so I'll ask you one of those. So we are always looking for water on other planets when we're looking for life. And shouldn't it be more likely that there's like life forming in organic stuff, like, I don't know, methane or something, than in water? So why is water the thing where life is forming?
So as far as we know, for all the examples of life we have, which is on Earth, life really, really needs water. It can get by without oxygen, it can get by without, or in really, really hot environments and really cold environments, but it always seems to need water. So as far as we know, you don't get life without water. That's not to say other things like methane or phosphorus aren't important, but water seems to be key.
Okay, so at least at the moment we don't know any other way of life. And that's also the answer to the other question that was sent. How many forms of life do we know? At the moment, only the one that we find on Earth. We didn't find any other life yet. But let's stay hopeful. And we got one comment on YouTube saying that Kepler-90 has 8 known planets at Martian colonists. So thanks for the note. So there apparently is a planet with more exoplanets. And we got another question. We got a few questions. Yeah, right. One about gravitational waves. Do you want to say something about gravitational waves, or should I?
I might leave that one for you.
Okay, so that's one of my the topics I like. So gravitational waves are a really cool thing, and the kind of idea behind this is that space can be kind of contracted and stretched and kind of pushed around. And what happens when you have massive objects like Earth or the Sun, they will kind of stretch space around them so that things will like orbit around them. It's the details don't matter that much. It's just that space can kind of be changed. And what happens is when you have two objects that orbit each other that are heavy or fast or close by or all of these things like black holes that orbit each other, is they send out waves of gravitational waves. So that's kind of a wave of space stretching that travels through the universe at the speed of light. And when it arrives on Earth, it also stretches and kind of makes space longer in one direction, stretches the other. So imagine I look at this door here on Earth, and when a gravitational wave passes through my room door here, it will go from 2 meters to like 1 meter and a bit. Well, the change will be really, really small. Like, I don't know, actually, I think it's less than a proton diameter of length change. So it's really immensely tiny, but there will be a change in the length of my door. And that's something, if you have really high-tech experiments, you can detect. So let me show you this slide. This is the LIGO observatory. So this is a gravitational wave detector. And what they essentially have is 2 really long arms with lots of lasers, well, with a big laser in them. And they use this laser to measure the length of the arm. And with this large arm and the strong laser, they can actually detect this really tiny change of length. And the reason you have 2 arms is you need to compare to something. So they take the 2 arms, compare their lengths continuously, and when a wave goes through the Earth, then one of the arms will be stretched, the other will be smaller, shorter, and then you can detect this. So that's how they find gravitational waves. And yeah, they get made when heavy objects like black holes fly around each other and finally merge. Can you explain how a spectral energy distribution is used to determine the type of stars in the galaxy? So essentially, let's say the color of the star. Yeah, do you know more stars, or should I?
So if you are assuming each star is a black body, then the peak of your spectral energy distribution will give you a sort of a wavelength at which it's emitting most light. And if you assume your star is emitting like a nice light bulb and it sort of has a characteristic shape, then you can use that peak wavelength to work out its temperature. And if you know the temperature of a star, then you can guess something about its age, I'm guessing.
I guess, like, I think the stars, aren't there like names like O star, D star, M star? Actually, I'm not sure if I'm using the right names, but are there like names? Are they related to the color of the star or the kind of temperature?
I think they are.
I think it's a mass, right? Yeah. Okay. I'm talking about things I don't know again.
Neither are really stars people.
Yeah, but essentially, a spectral energy distribution is a fancy word for color. I mean, it's more than that, but it essentially just tells you where in the spectrum of light is the most energy. So if you have a star that's really big, then it will be kind of bluish, and most of its energy will be in the shorter wavelength, which is blue light. And if you have a star that's kind of colder, more light will be in the red wavelengths, which makes, well, it a red star. And from that you can infer some properties, like primarily the temperature, and then you know kind of how stars work, and then you can infer other things like maybe mass, maybe evolution. I'm not an expert on this topic.
So I think the OBAG classification is based on magnitude.
Oh,
which is just
okay.
They look in the sky. So this is going back to when astronomy was very much an observational discipline. And so people would look at stars in the sky and say, this is a certain brightness.
Okay. Okay, I just noticed we have a lot of questions on sliders, so we should go through some of those as well. So one question, what got you into being an astronomer? Do you want to say something about this?
Yeah. So I really like computer coding and making models and making them do things and then making pretty graphs of the results. And I discovered this halfway through a physics degree at university. And it turned out that the way to do computer modeling in physics is to do astronomy. And then it turned out that space is just really cool. So that's why I stayed.
Yeah, I think it's similar for me. So, I mean, I started with studying physics, and it was just, I mean, my special discipline is cosmology, where I kind of got into from physics to cosmology and then to astronomy/cosmology, which is a discipline that looks at how the universe as a whole evolves, what are its properties, what it's made of, etc. And I found this just like the kind of most interesting thing ever. Like, what is this universe are made out of that we're living in? So I'm really happy that there's like, you can study this and you can make pretty pictures, and not only that, but also find out about the reality, and I don't know, find out how the world works. Yeah. We got a few galaxy questions. So we got a question about what happens if two galaxies collides, which is a really interesting question, I think. How galaxies are formed, and what the name of the oldest galaxy is. Okay, I don't know that much about galaxy formation. Do you know something about galaxy formation?
I think it's when you have clouds of dust and gas in a very, very early universe. And as they start to sort of, say you have a little bit that's more dense than any of the other bits, that will start to collapse gravitationally towards each other. And this happens on a whole load of different scales. So it's how you form stars. You have the beautiful large-scale structure of the universe, which demonstrates what I'm trying to show with my hands. Lovely.
I'm already taking a cut into cosmology here.
Yeah. So yeah, denser bits of the universe tend to get denser. And on small scales, those dense bits would become stars, but on much larger scales, they become collections of stars and dust and gas. And that's what our galaxies are made of.
Yeah, so essentially a big bunch of matter clumped together. One thing that's actually interesting, what I didn't know before I kind of got here and started working on my PhD, is that's actually kind of a bit hard to kind of collapse down into something that form a galaxy. So in the early universe, you have like lots of gas that kind of collapses, like gravity kind of pulls it together into kind of a blob of matter. But it's quite hot, so that's like the particles are moving quite fast. And for them to get into a smaller object, they actually have to cool. And in the early universe, this is actually a hard thing to do. So you have to kind of get rid of your energy, which you have to do by kind of emitting radiation somewhere. But it's not that easy, and you need like special properties to get this done. So then you can form galaxies, yeah. Oldest galaxy. I've heard of some galaxies that have like a redshift of 10 or so. And so that's a measure of how early something in the universe is. And I think this corresponds to 10 billion years, maybe a bit more. 12 billion, 11, so something like order, like a bit more than 10 billion years, I think, would be the oldest galaxy.
And do we know if that's the oldest galaxy or just the oldest galaxy that we've seen?
Oh, I mean, of course, it's always only the oldest galaxy we have seen. Given that the universe is 13.8 billion years old, I mean, there's a bit of space left, but certainly younger than 13.8, so somewhere in between. I suppose. And yeah, what would happen if two galaxies collided? Oh, I have the butter cluster here. Do you want to fly?
Do you have the picture?
I have the butter cluster picture. There we go.
Yeah. I'm not sure I can talk specifically about the bullet cluster.
Okay, that's the only one I have a picture of. But I mean, what happens in general if galaxies collide? So is it a problem for us if we collide with Andromeda?
I mean, for us personally, no, because it's not going to happen for a long time. But
that's true.
For our galaxy, almost certainly. So as you get two kind of massive collections of stuff colliding, they will get disrupted quite significantly. So our galaxy at the moment is quite nice and relatively neat, and it all orbits around a central sort of center of mass in a nice neat spiral. And if we crash into another galaxy, that's going to all get shaken up quite violently. And so we won't be a nice neat spiral anymore. We're going to look much more interesting.
Yeah, it's probably going to be a mess.
Yeah, it's going to be a mess.
I think we might be actually not that, like, on Earth it might be relatively, well, safe is a dangerous word, but I think like Earth will still continue to orbit around the sun, and maybe the sun might get kicked out out of its orbit and like fly somewhere. But I guess we will still stick to the sun, so it's not that immediately dangerous. One thing that might be there might be a lot of energy stuff happening, like gamma ray bursts and other explosions, which we would not like to have any in our neighborhood. So we have to take care, I suppose, when we go there. But yeah, otherwise, like, kind of when you imagine two galaxies, you might imagine a big clash or something. But actually, the stars are so far apart. So think of our star, and the next star is a light year away, which is really, really far away, relatively speaking. So when two galaxies fly through each other, actually, yeah, most of the galaxy just flies through. So that's one of these bullet cluster images, and it's a bit not completely like intuitive what you see here, but just look at the blue areas. So what happened is there, from left and from right, there came two galaxies that crashed together a long time ago. And what you see is on the blue sides, the blue marked regions, is where the most of the mass of the galaxy is, and it's kind of flown through each other. So in the center, there's a gas of the galaxies that is kind of stayed in the middle, that is like excited, and there was a lot of friction, so the gas kind of stuck and got slowed down. But the rest of the galaxies, so all the stars and all the dark matter, just flew through each other and came out on the other side. Well, not completely unharmed, probably a bit messed up, but more or less intact. So that's actually, yeah, not too bad, I would say, for galaxy clash. Dwarf planet. What's a dwarf planet? Is Pluto a dwarf planet?
Pluto is a dwarf planet.
Do you want to say something about dwarf planets?
Dwarf planets is where we put the things that some people want to be planets, but aren't quite planets. So I guess the easiest way to define what a dwarf planet is to say it's not a planet. And so for an object to be a planet, it has to meet kind of three criteria. So it has to orbit the sun, which is fine. Lots of things do that. It needs to be spherical. So it needs to be big enough so that its own gravity squishes it down into a nice kind of spherical shape. So it can't be a weird lump of rock. Like if you ever saw the images that the New Horizons probe sent back of objects in the Kuiper Belt, where there are all sorts of weird shapes, they are too small to be planets. But the third thing it has to do is it has to clear its own orbit, which means it needs to be giant enough that as it goes around the sun or another star, its gravity is enough to sort of kick out any other objects it might encounter. So that's why we don't orbit the sun in a disk of kind of other smaller objects, because the Earth is massive enough to have kicked out anything that was in the disk with it. And so a dwarf planet is something that's quite big, and we've seen, but it's not big enough, massive enough to have kind of met those three criteria. So there's quite a few dwarf planets in our solar system. Pluto is the most famous. And it's not a planet because it's not cleared its orbit. So Pluto orbits in the Kuiper Belt, which is a collection of sort of icy, rocky objects beyond Neptune. And so the reason Pluto was originally a planet was that we saw Pluto first because Pluto is very shiny, so it reflects a lot of light from the sun, which meant that people with telescopes could see Pluto long before they could see any of the other fainter objects that are orbiting around the sun with Pluto. So for a while, people thought Pluto was on its own, and so they called it a planet. And then as we got better telescopes and were able to look more closely at kind of the really far out parts of our solar system, we discovered a whole load of other stuff out there as well. And so it turned out Pluto wasn't as special as we thought. It was just quite shiny. and being shiny isn't enough to make you a planet, and so it got downgraded to being a dwarf planet. Yeah.
Okay, I think our YouTube chat somehow broke, so I'll just have to read them off from my phone, but it's fine. You'll just not see it on screen anymore, but don't worry, we're still getting your questions. So we got one question about age metallicity relation in galaxies, and I think this is Robbie specific. I'm not sure I'm able to answer that because that's not like nowhere near my specialty. But I'll give like a bit of general explanation. There's a thing that astronomers call metallicity. Actually, astronomers are kind of lazy people. So we call everything that's heavier than helium. So everything except hydrogen and helium we call metals because, well, why not? And the kind of main reason for this is in the Big Bang, only hydrogen and helium were produced, and a tiny amount of other stuff, but mostly hydrogen and helium. And so essentially everything else has to be formed within stars that get created at some point. Then they start fusion and fuse elements into bigger elements. Supernovae do this for even more elements, and kind of, well, when they die or explode, they just throw out all this material in the galaxy where they're living. So what we call metallicity is how much metals are there in a galaxy. And in the beginning, there were no metals because everything was hydrogen and helium. And then the first stars were burning and creating carbon, oxygen, nitrogen, all the stuff. So there was a bit more metal. And then we had supernovae, which also created lots of, well, all sorts of elements like gold and whatever. I mean, everything humans are made out of. And, well, not everything, but lots of things we need. So the galaxy gradually got more and more metals, and there is some kind of relation between how old the galaxy is and how much metals they have. I mean, intuitively, it's just if it's older, there were more stars, so you have more metals. But it's not that clear because I think there's like you could think that if the galaxy formed later, that it might have more metals in the beginning, and it's complicated. So not being an expert, I am not confident to say anything like any details here. But when we have a galaxy expert one day, I'll ask them this question and you can have a detailed answer. Okay, so we should take a few of the slider questions again. How do we get sun when Venus is blocking it? Yeah, did you observe the day when Venus went in front of the sun?
Was it Venus or Mercury?
Oh, I think it was both at one point.
Quite
in the last like 20 years. I think I saw one of them. So
I think it's on Mercury. Okay. So the answer to that question is because so if you were to look at the night sky and you look at the moon on the night sky, that's about the same as if you hold out your thumb at sort of arm's length. The size of the moon on the sky will be about the size of your thumb. And the reason that we get such cool solar eclipses is because the moon is about the same size as the sun, sort of on the sky. Mm-hmm. And that's because the sun is absolutely massive, but it's much, much further away than the moon. Venus is about the same size as Earth. So it's bigger than the moon, but it's not big enough that when it gets between us and the sun, it blocks out more than a tiny, tiny, tiny fraction of the sun's light. So the only planets that can pass between us and the sun are Mercury and Venus, because they're the only two that are closer to the sun than us. And our orbits have to line up in a very special way for them to get between us and the sun. So that doesn't happen very often, and it's called a transit of Venus or a transit of Mercury. And you can see it, but you can't see it as sort of the sun getting darker. What you instead have to do is kind of set up a very elaborate series of telescopes, because you obviously can't look directly at the sun.
Do not look at the sun. We had a discussion last time on the live stream.
Never look at the sun. It's bad for you. But if you set up a sort of series of telescopes and you project the sun's light onto a screen, and you sort of make it look very big and sort of spread out, you can watch a tiny, tiny, tiny dot sort of move across that screen as the planet passes in front of the sun. So you can see it that way, but you can't see it sort of in terms of it gets a bit darker when Venus gets in the way.
Yeah, I mean it does get darker, but you can't notice it because it's just so
enough to
tiny amount. Yeah, actually, I remember we had the kind of an event at the Institute where we had like telescopes set up for people to watch this. Yeah, that was cool, yeah.
That was very fun.
And we got a few futuristic questions. So, is it possible to use a black hole as a time machine to the future? Oh, that's a cool one. If okay, something about negative mass. So, if negative mass would give us anti-gravity, and if we could do that. And do you want to take one of those?
No.
Okay, I selected the question. Those are mine now. Well, okay, so I mean, the equation of gravity essentially has a term for mass in there. So if you would have something that would have negative mass in kind of quotations, then well, the force would be inverse, and you would have anti-gravity, I suppose. But there's no way we could, like, there's no idea how we could or why we even could have negative mass. So that's nothing practical in the near future. And right, oh yeah, the black hole one. Okay, that's cool. So time machines are actually not even hard to do. Like, time machines are really easy. Going to the future is super easy. You just need to be either going very fast or be close to a massive objects. Let me take 2 pencils. So I have 2 pencils here, and this one is traveling in time compared to this one, because this one is higher away from the Earth. And wait, which way around it was? Whatever. And one of them is going at a different speed, because being close to a massive object makes time go slower subjectively for you, and going faster makes time also go slower for you. So the people on the ISS actually travel forward in time, you could say, because time is going slower for them. Same if you're standing on Earth, time goes slower as opposed to, well, being further away. Like if you go to a tower or something, you would be edging slightly faster, but this is like really tiny. Like you wouldn't notice it at all. Like even for astronauts being on the ISS, I think it's a fraction of a second that they age less. But if you had a spaceship that could go close to the speed of light, or if you could go to a black hole and get really close to it without kind of getting spaghettified, you could actually like travel really fast in the future. Like if you would go at, say, 99% of the speed of light, and you would go there for, I don't know, a few hours, probably, I didn't do the math, but maybe days or years would pass in the real world. Actually, that's an interesting concept that they have in the movie Interstellar, if you know that, where the people are standing on the Mars, on the black hole, not on the black hole, but close to the black hole, where time goes slower for them, which is actually a real effect that would also happen in reality. So that's time machine to the future, always easy, always possible. Time machine in the other direction, we have no idea yet how to do that, and it would give you all kinds of paradoxons, so probably not possible. We got a question on Twitch, actually. Oh, that's our first Twitch question. So nice to know that the Twitch chat actually works. What powers X-ray sources that are not associated with active galactic nuclei, but exceed the Eddington limit of a neutron star or a stellar black hole? Oh, that's a hard question. So, the X-ray sources I mostly know are active galactic nuclei, which are essentially centers, galaxy centers, where there's a big black hole and matter is falling onto this black hole. And while the matter is falling on the black hole, it's losing kind of energy, and this energy is emitted in radiation, all kinds of radiation, and some of it, or actually a lot of it, is X-ray radiation. So that's a source of X-rays. Another one are X-ray binaries. Well, the name obviously tells you already that they're emitting X-ray, but usually they are like a neutron star or a black hole that's orbiting around another star. So actually most stars, when they're born, are born in binaries. So there's a kind of a cloud, and the star forms, and the cloud collapses into 2 parts, and you have a binary star. So two stars that orbit each other. Eventually, one of the stars will die and become a white dwarf or a neutron star or black hole, and then the gas from the other star will flow into the black hole or whatever, and also have the same process as with active galactic nuclei. So they will lose energy and emit lots of radiation, mostly X-rays. And there's this thing called the Eddington limit, which is in a certain case, when you have a black hole and there's matter flowing onto it, then this matter will emit radiation, so it will emit light and all sorts of stuff, and this radiation will push against the matter falling in. So it's actually a limit, because if you would push in too much matter, it would emit so much radiation that it would hold the matter back. So this is like an equilibrium where there's only as much matter falling in as is radiation kind of pressing out, so it kind of is the same force, and which is this limit. And under some circumstances, the kind of emission can, like, this is the limit for the emission. I think there's some cases where you can get over this limit, so it's, I think, not that like complete. But yeah, so I'm not sure what other X-ray sources there are, or which one are you referring to. But I suppose it could be like X-ray binaries or something that do that. I mean, other X-ray sources, actually, we have one on the slide there. When two galaxies collide, their gas will have, like, their gases get slowed down because they collide, and all these collisions produce lots of energy, which you can also mostly see in X-ray. So this is not a particularly bright point source, but it's kind of a broad region that emits X-ray, which is the red area you can see on this picture. So this red stuff here, that's the X-ray image. So it's a kind of fourth color image where the X-ray is shown in red. Yeah, and I think we're already skipping the YouTube questions, so let's go back and take a few of the YouTube questions. We got one question we already got twice, so I should answer it now. If there's anything quarks are made up of. So I should maybe, actually, I should talk about quarks, right? Or do you want to?
Everyone loves a quark.
Okay, so what's our universe made up of? I mean, lots of gas and particles, but what are the atoms are made out of? And atoms are made up of protons, neutrons, and electrons, mostly. And most atoms. Well, actually, all the normal atoms. All that we like don't smash together in particle colliders. And these protons and neutrons are made up of quarks. So each proton is made up of 3 quarks. We can find this out by essentially smashing them together and seeing what happens. And that's kind of what we came up with. And we didn't find anything yet that quarks can split into. Like when you smash together atoms, all you see is quarks. You don't see, well, you also see gluons and all the other stuff in this picture, but you don't see quarks kind of falling apart into something. So at the moment, our idea is quarks are just unsplittable. But on the other hand, the Greeks thought atoms were unsplittable. Actually, I think they didn't know about atoms, but one time we thought atoms were unsplittable, and then we split the atom. So eventually we might split the quark, who knows? But for now, we don't know what it's made up of. I mean, there's always string theory, which tells you it's made up of strings, but yeah, I'm not an expert on this. Oh, do you have some book recommendations? We got a question about books for newbie astronomers.
Ooh. It's good.
There was one book which was recommended to me by someone after the last live stream. So I'll just check this and tell you. But I didn't read the book, so I can't like say I can't vouch for it. But it was recommended to me. It's called The Astronomy Book: Big Ideas Simply Explained by DK. So that's one I heard of. But yeah,
I'm a big fan of the Feynman lectures. They're not strictly astronomy, but they are excellent physics lectures.
Yeah, yes.
Get them in book form, or I think there might be recordings somewhere.
Yeah, I mean, it's of course hard to like say what level of like what you're looking for. So I think it's just like you probably go better to like I mean I suppose it depends on if bookstores are open now, but just check with someone who's like expert in books and can tell you what exactly you're looking for. So if you're looking for something more sciencey, mathy, or something more focus on astronomy and less physics, there's something for everybody usually. We got a few more questions. In a star-Gauss supernova, because it runs on out of lighter. Okay, if a star-Gauss supernova because it runs out of material diffuse and then collapses onto itself. How does the supernova dust again collapse to form a solar system? Right. So how does the supernova stuff get out into the kind of medium to form solar systems? So yeah, I think the main idea is that if the star collapses, not everything like ends up in the star. So actually, I think many. Oh, that's also reminds you of the planetary nebula. So when a star collapses, usually what happens is kind of I think the inner part, or like if there's a supernova, like the kind of inner part of the star collapse, and like eventually you get a black hole and a big explosion, and this explosion will push away all the outer shells of the star. So all the metals and interesting stuff that's in this part of the star will be pushed out into the medium, and then will be able to like be there as dust and can eventually form solar systems or new stars. I think I'm not an expert on like formation of solar system and like disks. Yeah.
So I think it doesn't necessarily all expand outwards and then collapse back into the same point. So your dust from one supernova won't necessarily all come back to the same place and form a new system. It'll get mixed up with the rest of space.
Oh, okay, yeah.
Sort of contribute to whatever interesting things are going on there.
So you have kind of a cloud or like a bit of a region in your galaxy where there's a lot of star formation, and then there's a lot of mixing.
Yeah, I think. I'm not sure if that answers the question.
Okay, so we got kind of a follow-up question, I suppose. How will the extremities of the Oort cloud be affected if the sun goes supernova or would go supernova?
Will our sun go supernova?
I'm pretty sure it won't. At least that's my latest update. So it will go into will become a red giant and then just collapse into a white dwarf.
So I know people have done really cool simulations of what will happen to the solar system as the sun evolves. I can't remember the precise details, but we're toast. Mercury and Venus are toast. Mars might be toast. In general, as the sun gets much older and much hotter, eventually it will stop being a main sequence star and it'll become something called a red giant, which is much bigger. So it'll expand massively, and so the sun itself will sort of grow outwards, and when it does that, its effect on the rest of the solar system will change, and so all the orbits of the planets will get disrupted. So it's quite difficult to predict kind of exactly what this will do, but it will definitely mess up our solar system. So things might get thrown outwards, or things might get eaten by the sun. I'm not quite sure about the very, very edges of the Oort cloud because it's so far away. It might not really notice. But definitely stuff closer in will get kind of thrown about all over the place. And so we can see this there's evidence of white dwarf stars that have sort of strange elements on their very, very surface. And they shouldn't be there because things on a white dwarf should sink down to the center very quickly, which means if you see them on the surface, they arrived there sort of within hundreds or thousands of years. So whilst that star was definitely still a white dwarf. And so that's taken as evidence of sort of bits of your solar system, so rocks or planets that sort of survived the star becoming a white dwarf, but are now falling into the star and sort of polluting the surface. So they're called polluted white dwarfs, and they are very cool.
Indeed, a really cool topic. I didn't know about them before I arrived here at the Institute, and that was, I think, one of the first talks I heard, and was really fun, really cool. Right. Yeah, let's just take some. Oh, wait, no time machine question. How could we ever get out of a wormhole? And like a time machine. Well, directly, we talked about time machines already a few minutes ago. Wormholes, we don't know if they are wormholes. Could, in theory, like mathematically, there could be wormholes. In practice, it would be like hard to make wormholes. Like there are a lot of kind of practical issues. And in particular, traveling through wormholes is kind of futuristic, like even if they would be there. So for now, I'll go with I don't know. Not now and not in the near future. But maybe if there are wormholes, and if we find them eventually, and if we find the technology to kind of do something with them, well, then we might eventually have fun with wormholes. How do black holes start? We kind of just discussed supernovae. Do you know a bit more about how they make black holes?
So I guess if the star you start off with is big enough, then it goes through a series it burns hydrogen like the sun is doing now into helium. So this is fusion, where you take a light element and you turn it into a slightly heavier element, and that releases some energy. And so the sun will keep burning hydrogen until it sort of is no longer energetically favorable for it to burn hydrogen, and then it'll kind of, the inner part will collapse, and then the center of the star, which will then be full of helium from burning all the hydrogen, will get hot enough to start burning helium into carbon and oxygen and nitrogen. And then sort of, if your star is big enough, you can end up with a sort of a core of carbon and nitrogen and oxygen that then collapses and is heavier enough to sort of burn and turn into heavier elements. And this can carry on and carry on and carry on until you get up to iron, which is the kind of the heaviest element that you can make in a star as it's undergoing fusion. And sort of, if your star is massive enough, then once it's gone through all those burning stages, you end up with an incredibly dense core. And if that core is dense enough, so if your star is massive enough to begin with, that it can have enough stuff to have a core that is dense enough, you then get to the kind of black hole limit. So a black hole is just something that's so dense that its gravity is so strong that light can't escape. Do you want to add anything?
Well, no, I think that's a really good explanation. So you have kind of a star that's made, well, that's just heavy enough eventually, and then eventually whatever is in the center after this kind of collapse will be heavy enough to be a black hole. Yeah, that's pretty much it. Actually, there's like, yeah, another way to make black holes is when you have a white dwarf, and actually a neutron star. A neutron star, so that's kind of heavy, but not heavy enough to be a black hole. Like it's barely kind of below the limit for black holes. And then you could have a second star being close to it, feeding gas on it, feeding and feeding and feeding. And eventually this neutron star will grow and grow and grow and, well, get heavier and heavier. And eventually it will be so heavy that it collapses into a black hole. So it can no longer kind of, the pressure of the actual, I think it's neutrons, like the neutrons, like it's made of pure kind of neutrons. And even that pressure isn't enough anymore to stop the gravity. Then it just collapses onto itself and, well, also forms a black hole. Which is really cool because this is really predictable because it always happens at a certain mass, the so-called Chandrasekhar mass, which is 1 point something solar masses. And that's why this explosion that you get then, so the supernova, it's called type 1a, is always the same brightness, or well, more or less the same brightness, which is a really nice feature you can use to measure how far away some things are in the universe. Supernova cosmology is a big field, but I won't start a discussion now. Oh, what's the cause of the observed acceleration of the universe? And that's also a cool question. I suppose that's one for me again, because that's my cosmology question. Right, so what we observe is when we look out in the universe, stuff expands. And that's not really that surprising. So when you have an explosion, like a Big Bang, stuff will start expanding and will just continue expanding unless something is stopping it. And what you would expect is, okay, the expansion curve slows down. Like when you shoot, like, I don't know, imagine you have a cannon and you shoot really, really fast with, I don't know, a few tens of kilometers per second into the sky. The ball will fly up there and then get eventually slower and slower, but will continue to fly. And you would expect the universe to get slower as well. And it did so until a few billion years ago, where it suddenly started to expand faster and faster. And we found out, I think in the 90s, there was actually a Nobel Prize for this discovery, which with supernovae, there we go. Supernovae were used to kind of measure this expansion. And yeah, so we found out the universe is expanding faster and faster. And well, this is within the limits of our kind of mathematical equations. So general relativity tells you, yeah, there could be such an effect. We just didn't expect it before. We thought, oh, surely this is zero, where it turns out not to be zero. And people also think, okay, it might be either this kind of purely mathematical effect, but it could also be that's kind of the same idea, an actual physical like stuff that's in the universe, which we call dark energy. We just call dark everything we don't understand or don't see, or both. And it would be something that when the universe expands, doesn't dilute, which is a really weird property, which is why dark energy is really weird. But yeah, that is what makes the universe expand faster and faster. Yeah, and we are in this kind of faster and faster expansion phase since not that long ago. I think like Redshift 1, which is still a few billion years, I think, but yeah, since then I think it was before we had life on Earth, but not that much before. Okay, so we got a few more questions on Slido. In the nearest solar system to us, do you really know what the planet looks like because it's the closest? Right. So the nearest solar system to us is now I'm not sure if I'm getting it right.
Proxima Centauri.
Yeah, right. This one.
Yeah.
And I think it has a planet, doesn't it? At least
it does.
Okay.
Proxima Centauri B.
B. Okay. Yeah, I think is B, like we always start with B, right? With planet names. Okay.
Yeah. So the star gets to be
A. I see.
We never call it.
Do we know much about that system?
So we know it's a super Earth, so it's bigger than Earth, but not as big as the gas giants in our solar system. So things we can know about exoplanets are pretty much their mass and their radius, and if we're really lucky, we can estimate a temperature. For things like hot Jupiters, so things that are a bit like Jupiter in our solar system, but they're very, very close to their own star, we can sometimes get estimates on what's in their atmospheres. But for something like a super Earth, so something much more like Earth or Venus or Mars in our solar system, at best we can get kind of good estimates on their mass and their radius and how far they are from their host star. And from that, we can estimate how hot we think they're going to be. So we know stuff closer to the star is generally hotter. So we never really know what they look like. So when you see a beautiful kind of picture of an exoplanet, like these ones for the TRAPPIST system, they are artists' impressions of what they might look like. All we really know is how massive they are and how big their physical size. So we can estimate kind of from their bulk density whether we think they're maybe made of iron or rock or water. So someone had a question about planet which is completely water, which I don't think is physically that likely, but you can get planets that have a sort of rocky core and then massive oceans. So like nothing in our solar system, but they're called water worlds or aquaplanets. And they're kind of a theoretical possibility. And we've got some candidates for them. But they can be really interesting in terms of kind of what happens if you don't have any continents on your planet. Yeah, so I guess the answer to that is we don't know what they look like, but we like to imagine because that's fun.
Oh, okay. So we have two big questions left over: the Great Attractor and the Fermi paradox. So let's start with the Great Attractor, because last time I wanted to do it and the show was over. So this time I will fulfill my promise and talk about the Great Attractor, and afterwards we'll try to squeeze in the Fermi paradox. The Great Attractor, which is a really cool name for a phenomenon that we observe, and what people did is kind of look around. So this is a picture of one of the many galaxy surveys that have been done, and they found kind of where are galaxies, where are kind of big clusters of galaxies, and this is a kind of a 3D map of this taken from Wikipedia from this person. But yeah, that's of course real data. Anyway, so I mean, of course, people also have been giving these structures names, and we have been observing where are they moving. And so the interesting part is now that we observe that our solar system is moving relatively fast in one direction, and not only our solar system. Well, I mean, this is just like circling around the galaxy, but our galaxy is moving, and not only our galaxy, but the local group and the cluster that we're part of. So I think it's called, let me check, the Virgo supercluster. So that's kind of the bigger unit of nearby galaxies that we are part of, is moving towards one direction, and we don't exactly know what's there. The main reason for that is it's towards the galactic center, so it's really hard to observe with telescopes because there's just lots of stuff in the way. So people just started talking the Great Attractor and just, okay, everything's moving in that direction, so there must be something great attracting this. Eventually people started giving the stuff more names. So yeah, there's the thing that people call Laniakea supercluster, which is actually a supercluster out of superclusters. So I would rather call it a supercluster, but whatever. And that's kind of everything that's around the Great Attractor. So there must be some mass well, in that direction galactic center, and how far away? I think like a few hundreds of megaparsecs, so a few hundreds of millions of light years away from us, and that's kind of the direction where there must be a lot of mass at this point, and that's where most objects are moving, and that's kind of a one kind of big cluster where stuff is gravitationally bound. And then there's like there are multiple of those clusters we can observe, and you always have this hierarchy. Like you have small clusters, and you have bigger clusters, you have bigger clusters of bigger clusters, etc. Until eventually you get to what we call the cosmic web. So when you would you can't observe this directly. So this is a simulation. Actually, it's a Millennium simulation, which was a cool project. And what you see here is how would the universe, kind of a slice to the universe, look like on really large scales. So what you see there on the scale, this are 500 megaparsec. Well, actually, it's like 700 megaparsec, but don't worry for now. So this is, well, a few, like 2,000-ish light years, 2 billion light years, this distance. And the universe, you wouldn't see one big cluster, but instead you would see kind of a web of structure. So if you zoom out far enough, you stop seeing like one massive thing, but you just see a more or less homogeneous mass or distribution. Like there are like some filaments and some clusters and some voids, but it's kind of more or less evenly distributed. Like if you imagine you smooth this image on a few hundred megaparsec scale, you would see just a uniform kind of density. And that's kind of one of the main ideas behind cosmology, that our place, or in general, there's no special place in the universe that's particularly dense if you zoom out far enough, but that everything is more or less the same. Yeah, so that's from the great attractor to the universe. The next one Twitch question we got recently: is there other life in the universe? Especially, is there other intelligent life? If so, what is the explanation for the Fermi paradox? That's a really nice question. Do you want to answer, Kat?
Sure. So I guess firstly, the Fermi paradox. What is that? So that's this idea that if there was intelligent life in the universe, why haven't we found it? So we have no evidence at all for intelligent extraterrestrial life. We have no evidence at all for any kind of extraterrestrial life. As far as we know, we are alone. And so the Fermi paradox basically states that if there was intelligent life, why haven't we seen it? Sort of the universe is so big that if life could have occurred on other planets, it should have somewhere, and so why haven't they been and said hello? So there's been lots of kind of potential explanations for the Fermi paradox, which range from the kind of very pessimistic, intelligent life really doesn't last that long because it tends to either destroy its planet or blow itself up in a nuclear war, or sort of otherwise cease to exist and stop being intelligent life quite quickly. And so there might have been lots of intelligent civilizations, and they just never overlapped.
So one question that I kind of would ask is why would we expect to kind of find, or like life to find us or reach us? Like why? I mean, maybe there is life on one of those planets. I mean, surely we wouldn't be able to see it, right?
Yeah. So I guess the further away life is from us, the more technologically advanced it needs to be for us to be able to know it's there. Yeah. So it might be that we're just not technologically advanced to see it.
Well, yeah, right. On the other hand, when I think like about how far, like imagining, okay, we have like been, I mean, when did we discover space flight? Like, I don't know, less than 100 years ago, kind of. Yeah. And we got to, I don't know, the moon and soon Mars. And like, given that, I don't know, the universe is billions of years old, the galaxy is billions of years old. So like, there must be other planets. Like, I mean, our planet is billions of years old. It would be like say you give us another 1,000 years, humanity. I would expect we would have colonized a few stars, maybe. Well, maybe at least our solar system. A few 10,000 years, probably other stars. A million years, probably, like, I don't know. I would expect us to kind of go further out and probably have the whole galaxy. And given that there is like a billion years time, has been a billion years of time, if there was someone else, they could, I mean, I would expect them to kind of have colonized the whole galaxy, including us. So that's like kind of always my view on this Fermi paradox thing.
Yeah, I think
if there was other life.
Yeah, that's the question.
And it was there kind of not at the same time as us. I mean, it might be that they started at the same time as us, but I mean that would be kind of a coincidence.
Yeah.
Yeah. Okay, sorry, I brought you back off the topic.
Yeah, it's
right.
Yeah.
So you were
It's a
discussing.
very interesting question, but
Yeah. So you were discussing like what reasons would there be for life not to be for life not to kind of find us. So like life could destroy itself, or there might be some other barrier stopping it from, well, finding us or contacting us or something.
Yeah, I mean, it could be that it's too far away. It could be that actually it doesn't exist at all. It could be that it existed long before us, or it's not existed yet. Or you get kind of slightly more out there ideas that are sort of, it is out there, but they're deliberately choosing not to contact us. Maybe they had a look and decided they didn't fancy it, so they stayed alone. Or they're treating us as a kind of zoo or like a wildlife sanctuary, so they're just leaving us on our own to do our own thing and deliberately not contacting us. But these are all quite hypothetical ideas.
Yeah. So I think I mean I personally I wasn't sure that there is other life in the universe. I'm also quite sure there's not in our galaxy yet. So I mean the
universe is so.
I mean, the universe is probably infinitely large. I mean, we don't have any reason to believe otherwise. And if it's infinitely large, I'm sure there is life somewhere. It's just really far away. So we have like the question: is there life that can ever contact us? Is another question, but I'm sure there is some life somewhere. Yeah, I think there was also a paper that kind of calculated like, is it really that surprising if we would be the only like planet with life in the galaxy? And it wasn't that unlikely. Like, it could.
So there's the kind of the famous Drake equation. That attempts to tell you how many intelligent civilizations there should be by multiplying together a whole load of probabilities for sort of how many stars are there, how many of those stars have planets, how many of those planets could have life, how many of those possibly habitable planets got life, how many of those life things became intelligent, how many of those intelligent life things sort of existed long enough to overlap with us. And if you ignore the fact that we don't really know what those numbers are for most of the terms in that equation, you can multiply them all together and get a probability for a number of sort of intelligent civilizations that should be able to say hello to us. But the big problem is that actually we don't really know what the values are for a whole lot of those terms. We're still working out kind of what makes a planet habitable and how likely you are to get life if you sort of just let a planet that could have life, we think, sit there for long enough.
I think that's something we astronomers do often, like take a bunch of things we don't know, multiply them all together and say we only have one thing we don't know. We're doing this in my field as well. We have the star formation rate and the efficiency of stars and the fraction of photons escaping, and we all multiply them together and call it efficiency, and then it's just one thing we don't know. But actually it's just a lot of things we don't know. Okay, let's take like one more question or so before we stop. Because there was one, why do larger stars have shorter lifespans, which is a really interesting one. So, yeah, do you want or should I?
Do you have a strong feeling about this question?
Well, I'm not a strong feeling, but I heard the answer. Okay, yeah, so the general kind of rule is that larger stars burn much faster and much brighter, which means they just burn through much more mass than small stars. So even though they have more mass to begin with, they burn through it much faster and die earlier and live less long. So actually, when you have a really small star, I'm not sure, I think a bit less than solar mass, they would have a lifetime longer than the lifetime of the universe. I remember correctly. Yeah, like the sun has a bit over 10 billion years lifetime, I think. Well, actually, 15?
We're halfway through, so it's 9 billion, I think.
Okay. And yeah, there's some stars that are smaller that have an even longer lifetime because they're just burning so little stuff. So that's why they live so long. Okay.
And dwarfs. Dwarfs.
Oh yeah, they're called dwarfs. Of course, we call all the things dwarfs. Yeah.
We like our dwarfs.
Okay. Yeah, then this is already 8 p.m. In Europe, or 7 p.m. in the UK, or 2 p.m. in Eastern Time, 6 p.m. Universal Time thing. That's all I can say from my heart. Thank you all for watching. Thank you, Kat, for answering all the questions and being here.
Thanks for having me.
Yeah, thanks for all the questions and all the nice comments and the corrections in the chat. You can join us again next Monday. We'll be here again answering all your questions. There's also other things on this YouTube channel. So Tuesdays, usually, there's a live stream from one of our outreach people who was like giving a lecture kind of about a topic. You can check out on the YouTube channel. It should be announced now. And yeah, otherwise, thank you all for watching. And see you next week.